Hi, this is Timothy Malloy with video 3-1 on what is this? Wire magnetic fields. This is problem 12 from WebAssign 11A. Okay, so problem goes, two long parallel wires carry currents of, oh wait, is the pointer working? Let me double check and see the point. Okay, so the pointer's not working. Oh no. Okay, I'll just use the pen then. Okay. So two long parallel wires carry currents of I1 equals 2.6 amps and I2 equals 4.7 amps in the directions indicated in the figure below. So that's out of the page, out of the page. And then this distance between them, D equals 21.5 centimeters. So let's just focus on problem A first. And they first ask, find the magnitude and direction of the magnetic field at a point midway between the wires. Okay, wire 1, wire 2, midway between the wires would be this point here. So I'm thinking, okay, where does the magnetic field point? And we see, I like this arrow example. That kind of, helps you understand which side is which. So if our arrow has a little tail here and a pointed edge on the one, when we see the pointed edge coming at us, then the arrow or the magnetic field is coming out of the page. And then when we see the tail, we see that the magnetic field is going into the page. And I just have it scratched off here because in this example, they tell us it is coming out of the page. I know, they already told us it was coming out of the page, but that's just my justification for it. I thought it'd be important to include in the video. And then it comes out, so the field travels counterclockwise, or I like to call it like travels like with the unit circle, but I guess that's just something I think about because I have, it's a good pairing to put the physics with the math because that helps me understand it. So I redrew that those two wires down here, I1 and I2, I gave them colors just so we know which is which. And so we see that because they both have currents traveling in the same direction at this midpoint, the currents or the magnetic fields actually oppose each other. I mean, the magnetic fields travel in opposite directions, but magnetic fields oppose each other. Anyways, again, opposite directions. So if we can subtract, okay, also I2 is greater than I1, by the way. So if we subtract I1's magnetic field from I2's magnetic field, we'll get the positive difference. I have an explanation for that coming up in a minute, but that was just something I wrote down. So we know magnetic field equals mu naught times current over 2 pi r. Mu naught is a constant equal to 4 pi times 10 to the negative 7th Tesla meters over amps. Again, traditional formula from Lab 2-8. And it again proves my thought that B2 is greater than B1 because I2 is greater than I1. Bigger current magnitude, bigger magnetic field. So again, if we subtract the bigger magnetic field from the smaller one, positive difference, of course. And so what I did is this is I2, I believe. Let me just double check. Yeah, because I2 is greater. So this is I2, this purple, and I1 is the blue. We plug in our known currents for each, our constants. And then for the distance, we use d over 2, because the total distance between them is d, and then d over 2 equals this about 0.1 meters. So simple subtraction, put it in nanoteslas, we get 3.1 nanoteslas. And then at this point, the magnetic field points straight down, and I guess up, but again, the net faces down. So our magnetic field points 270 degrees counterclockwise of the x-axis. So we'll go down and check that. 391, all good. 270 degrees, all good. Okay, that was pretty basic to part A was pretty easy. You don't even have to use like the right hand rule because they really give you they give you what direction it is, and then just I guess from lab notes or whatever which way the current travels. The magnetic field travels, sorry. Okay, so then I'll go on to part B now. So part B says find the magnitude and direction of the magnetic field at point P, located the same distance, D equals 21.5 centimeters, above the wire carrying the 4.7 A current, so above I2. So what is the magnetic field at this point P? This one is a lot harder because you're going to have to use some sort of trigonometry with the fields acting and whatnot. I will get into that now. So again, we need some trigonometry witchcraft. We already know where we can deduce or infer whatever that the magnetic fields due to wire 2, so B2 equals 4.37 nanotesla. That's because we used this formula up here, except for distance, since I2 is a distance d, like they said, away from P, and not just a distance d over 2. We have to, oops, we just use this, just plug in all these numbers again, except we multiply by 2 to compensate for that d over 2. So again, I did all that, and then that is how I reached 4.37 nanotesla. Again, distance doubled, whatever, you get it. Anyways, so again, think at point P, both fields want to rotate the point counterclockwise. They both want to. And then you can see this purple one, since it's, what would I call this? Cardinal direct, perfectly like, it's perfectly above the wire, so it wants to go straight left. Whereas this one is not straight above the wire, so it's kind of 45 degrees pointing northwest. Yeah, okay. So then that's where the blue comes from, that's where the purple comes from, and then BF is my resulting magnetic field. So I hope you can kind of see that BF triangle, and then it'll have components. I guess the only Y component will be from I1. I'll call it B1Y. But then this X component will be from both wires. I'm just explaining this a lot because it took me a little while to understand myself. So I guess I'm also explaining it for myself here. So um, if I just isolate I1, I guess if I just focus in on that, you can see again. We actually have a distance, which is d over 2 or d root 2, because 45, 45. 90 rules right here. And then, so that's our distance that we're going to be using in our formula. And then make sure to note that we have X and Y components again. And with I2, it's just the X component. Okay, so here we go. So I named BF our final magnetic field. So BF of X is going to be equal to B2 again, which is all B2 only has magnitude in the X direction. And then I add my current from I1 to the point, which is using I1's, or my field. I think I correct myself every time I confuse field and current, but anyways, here's our resulting field from I2 in the X direction. We plug in our known current, we plug in our distance away, and then we have to multiply by cosine 45, because that will give us the X components. That will give us the X component of our of wire one's magnetic field. Yes, that makes sense. Okay, so because this is just I'm pretty sure this is just BF. At least no, this is just B1. This is just B1. But we're extracting the X component when we use cosine 45. So then if we add B2, which is all X, and then B1's X component, we can get the final field's X component, which is 5.58 nanotesla. And then for BF of Y, because magnetic field from wire 1 is that only has not that has a vertical component, whereas B2 doesn't. There's no adding of B2 in this one. So this one again is just total B1 magnitude, and then multiplied by sine 45 to, I guess, isolate or get the vertical component. I said that really slow because I myself was having trouble understanding. But anyways, we have our y component, we have our x component. We know why each is each. We can Pythagorate that to get uh, the resulting field with, again, B2, B1's, no, you know what, you get it. It's B2 and B2, which has x component, B1, which has x and y component, yada yada, 5.71 nanotesla. And then for angle, pretty easy, uh, opposite over adjacent. If we, make our BF triangle, X, Y, you understand that, very easy. And then our theta is 12.2 degrees. They ask how much degrees that is when we rotate it counterclockwise from the positive x-axis. And then you can just do 180 minus theta, which is 168 degrees. Okay, so that is the problem. And then here's my proof. It's all correct. And takeaways is that last part is tough to explain, at least for me. I think I did an all right job. I think I hopefully didn't confuse my words, and you kind of understood that one current is different from another, and just the nature of doing the trigonometry. And then hopefully the drawings were okay, because that's really important with all the rotating and which points where and everything. And hopefully the explaining was fine. So thank you, and have a good night.